So here's an example of propulsion. I decided to make one that was a little more challenging in some ways, but also was a great example of conservation of momentum. Now, as you know, momentum is the mass times the velocity of an object. Momentum in a closed system is conserved. Whatever you had before, you will have after. And it's easier to calculate in the other form of this equation, this form. Okay? So I decided to design this problem so that we would have to use it this way, and there's an additional difficulty level here. Okay? So we're talking about a rocket in intergalactic space, not just interstellar. I'm going full intergalactic. Now, we have barely reached interstellar space with Voyager 1 and Voyager 2. Those are the only spacecraft we have that are outside of our solar system, just barely, just outside. So I guess they're in interstellar space. Going to intergalactic space is something that we may never do, but I thought that would be a great place to set one of these problems, because then we could truly say that you would be so far from any gravitational field that they would be negligible, for real, okay? And we're talking about a rocket. Now here's the issue. The rocket contains the fuel. So when the rocket burns its fuel, okay, the mass of the rocket will change. So I deliberately made the mass of the fuel that was expended so great that you couldn't just ignore it. Because a lot of times we do ignore that difference, as I did in an earlier example, if you didn't notice. Didn't notice that? Well, I did. So I decided to make these close enough that we couldn't just ignore the difference in mass. Okay, so here we go. Now the thing about this is a conservation of momentum problem, but I didn't want to start with a velocity of 0. Why not? Because if you start with a velocity of 0, then you start with a momentum of 0, and then you might as well just use this. So I wanted to do one where we did not start with a velocity of 0. We do have an initial velocity. This one would be right there. Let me write it in. This would be our VI. Now, which VI? Is it for A? Is it for B? The answer is yes. So remember that when the rocket is traveling at the beginning, the fuel in the rocket are 1. Okay? So even though I've made this problem a little trickier in some ways, there is one thing that's easy. These two combine into 1. Okay, so you don't have to worry about A and B until the rocket and its fuel are separate. Well, let me just read the problem, okay, just so we're clear on what we're talking about here. A 4.2 times 10 to the 6th kilogram rocket traveling through intergalactic space at 8.0 times 10 to the 2nd meters per second expels 6.0 times 10 to the 5th kilograms of gas at a velocity of negative 5.1 times 10 to the 3rd meters per second. Negative, huh? What is the final velocity of the rocket after expelling the fuel? So let's imagine this is our rocket and it's going in one direction. Okay, so if we draw this and the rocket is going that way, the gas is ejected at a velocity of negative 5.1. So we know that this direction is going to be negative, this direction is going to be positive. I don't know if you can see that clearly. This is positive, this is negative if we're talking about the rocket. Okay. So why don't we use this equation? The only major difference is going to be, first of all, that the mass at the beginning is the combined mass. You could sort of say, how about this? We'll call it the mass of A plus B, okay, times VI is going to equal the mass of A, we'll do it that way, times VAF plus the mass of B times VBF, okay? See what I mean? So VI is just one number. So VI is this. And then what is this one? Well, if we consider the rocket A, we'll consider the rocket is A, the fuel is B. Okay, the gas is B. Okay, so this is the velocity of the gas. So this would be VBF. That's the final velocity. And what we're solving for, the final velocity of the rocket, well, that will be VAF. That's what we're solving for. So this is the one we're solving for. I guess I should have written that in green. I was trying to be consistent here with greens and blues. Oh well. So that's what we're solving for. I'll make all the velocities green. Okay. So this one is one that we know, and this one is one that we know. So let's just write in the ones that we know. Okay, so the mass of A plus B is this. So let's just write that in right off the bat. 4.2 times 10 to the 6th kilograms. Is that the correct unit that we need? Is that the correct unit that we need for all this? Yes. Yes, it is. And what is the velocity? The velocity is 8.0 times 10 to the 2nd meters per second. Okay. And what does that equal? Okay, now this gets to be the tricky part, because we actually do not know MA, okay, but we do know MB. So if we want to find out MA, well, let me move this now, okay, maybe I'll do it up here. MA equals MA plus B minus MB, right? So what will that be? So MA, I'll do capital A equals this mass, 4.2 times 10 to the 6th kilograms, minus MB, I should write it right here, huh? This is, well, I don't want to write on this one. I'm just going to write it on the edges. So this is MB minus 6.0 times 10 to the 5th kilogram. So I deliberately made these close enough together that this would be significant, that you couldn't just ignore that, okay? Now, how do we subtract numbers that are in scientific notation? Well, one way to do it is to put them both with the same exponent, okay? And if you do that, you can just subtract them like you do any other number. Now, what is usually easier to do is put them both in terms of the lower exponent. So what would this be if I were to turn this into 10 to the 5th? Well, if it was 4.2 times 10 to the 6th, then it would be 42.0 times 10 to the 5th. See what I did there? I moved the decimal over 1 and changed the exponent. I kind of took it out of proper scientific notation. I did the reverse, put it into improper, so that it would have the same exponent as this one here. Because remember, 10 to the 6th is one position over from 10 to the 5th. So now it's just 42 minus 6. That's easy. That's 36, right? Let's just double check. Minus 6, 36. So this equals, so MA, now we have it, equals 36, but you know what? Okay, I'll write it this way. 36.0 times 10 to the 5th kilograms. And let's put it back into proper scientific notation now. Come on. 3.6 times 10 to the 6th kilograms. Okay? So notice that is significantly different than this was. That's significantly different. That's the reason that I made these so close together, so that we couldn't just ignore. Sometimes the amount of fuel, if your mass is in kilograms and your fuel is in grams, well, you can probably just ignore it. That's what I did in a previous example. But here I wanted to have it actually matter. So see what I mean? This is the combined mass of the rocket containing the fuel, but then once the fuel is lost, the rocket itself will have a lower mass, having lost the mass of that fuel. Now, by the way, we aren't talking about specifically what chemical reaction this is. We're just assuming that let's say at least the average velocity winds up being this of the gases that are expelled. Okay, but you're assuming that this is due to some chemical reaction, but we're not worrying about what that is. All we're worried about is the mass of the particles and how fast they're going. Okay, so then we've got this one, 3.6 times 10 to the 6 kg times VA, which is the one we don't know. VAF. VAF. That's the one we don't know. Okay? And that's going to be plus numbers that we do know. The mass of the fuel, how much gas was expelled, right there. 6.0 times 10 to the 5th kilograms, right? And do we know the velocity of it? Yes, we do. And this is where it's important to make sure to get the negative sign. Okay, now I could have put positive signs there, but even if you forget that, it's not the end of the world, but it is the end of the world if you don't put the negative sign. Negative 5.1 times 10 to the third meters per second. Okay, so let's move some of this stuff out of the way. Okay, and we're going to multiply where we can, and then we're going to solve. So let's simplify, let's combine these, and then we'll rearrange it after that. Okay? And for this one, because it's m times v, I'm going to write it in purple to represent the momentum. Okay, so 4.2 times 8 equals 33.6 times 10 to the, what would it be? 8 kilogram meters per second. Okay. Now, of course, this is not proper. Okay, we don't have to worry about that yet. Let's first do it for all of them. Okay, now this one is still a mass. I'm going to keep it blue. 3.6 times 10 to the 6th kilograms. There's not much we can do with that right now. And this is our unknown variable. This is the one we're solving for. This is the one we want to get on its own. And then it's going to be plus. Now over here, we've got 6 times 5. Okay, so we'd expect it to be 30, but it's not exactly. It's 6 times 5.1, so 30.6 is it? 30.6. 30.6. Oh yeah, and of course, negative times a positive is a negative, so let me put it in parentheses just to make that clear. Negative times positive is negative, right? And 30.6 times 10 to the, what would this be? Oh, interesting. Also 8. And also kilogram meters per second. Interesting, interesting. Okay. So now what we can do is we can get rid of this, first of all. We want to get VAF all on its own. We want to isolate it. So we have to get rid of all of its roommates. It's living in an apartment building. We have to get rid of each roommate separately. First, you want to take away what is added or subtracted. So this is subtracted on. This is the weird, it's plus a negative, right? So in order to get rid of that, I actually need to, let's say, add it in. It seems weird because it's a negative number. So what I would do is if I add that to both sides, get it? So let's see, where can I write that? Okay, I'll just do it very, very clearly. I'll write 33.6, just so that there's no confusion. 10 to the 8th kilogram meters per second. So it's going to be plus, because we're actually, think about what we're doing. We've got a negative number, so we have to add it to both sides to get rid of that, right? We have to add that. So it's plus 30.6 times 10 to the 8th. So notice I haven't even bothered putting it in proper scientific notation. This is a little bit sloppy, but actually you're going to see, I think this is going to save me a step. Looking at this, I think it's going to save me a step. Okay, so 3.6 times 10 to the 6th kilograms. And then we've still got that attached to our VAF, which is the final velocity of the rocket. Okay. So 33.6, I've still got the 30.6 on here, so I'm just going to add it, plus 33.6 equals, okay? Oh, it's not going to save me a step after all, is it? Okay, because I was thinking the other way around, wasn't I? I was thinking if subtracting it would have saved me a step. So I still have to fix this. 64.2 times 10 to the 8th kilogram meters per second. So you know what, I'm just going to let this play out. Since I already didn't put it in proper scientific notation here and didn't do it here, I'm just not going to do it here. I'm just going to do it when we get closer to our answer. I'm crazy. I'm acting crazy-like. Okay, and then that equals 3.6 times 10 to the 6th kg, right? And that's our VAF. Okay, so now, how do we get our VAF all on its own without roommates? Well, obviously, you have to divide both sides. You have to divide both sides by the same exact number with the same exact unit. Okay? To do it on both sides, to be fair. Now back here, I didn't write it on both sides. Hold on a second. Back here, I didn't write it on both sides because I assume you realize that if I were to add this over here, that's why that disappeared. Okay? So I did not show that part. I just thought that that was obvious. But with division, I think I'll just make sure to show it. And then right here, well, obviously, this stuff we expect all of, what color can I use? I've used all the colors. We expect that's going to cancel. Obviously, the unit's going to cancel. Whoosh, that's just gone. And so 64.2 divided by 3.6 equals, well, it's still a double-digit number. So in the end, doing all this didn't really save me much work, did it? I was hoping, but no. So we got over here, I'll put it in green, 17.83, and the 3's go on forever, but don't write those because you got to limit, you got to round off your answer to a reasonable position. These are approximations, even in intergalactic space. And then if it's 10 to the 8th divided by 10 to the 6th, what do I get? 8 minus 6, 2. Kilograms cancel kilograms, meters per second. Okay? And this equals what's left on the other side? Only VAF. So you might think this is my final answer, and it would be, that is the unit of velocity, but it's not proper, so I'm just going to write that final answer. Oh, I've got room right here. I'll just write it right. I'll write it over here, just so there's a nice space for it. So VAF, I'm going to write it again, equals, I got to move that over by 1. Remember, if you move the decimal over by 1, then that adds 1 to the exponent. So then I get 1.78, notice how I'm losing that 3, I'm just rounding to there, times 10 to the, what would it be? What would it be? 3rd meters per second. Okay? And is that positive or negative? Just because it's probably important to say whether it's positive or negative. What is it? Remember, the rocket was defined as going this way. We defined that as positive, and the fuel was going negative. So I'll just put the positive sign. Or the other way to say it is traveling through intergalactic space. So it was going forward. I could also say forward, because that's obviously the direction the rocket was already going. It's just going even faster in the same direction, so I can define that as forward. And then I want to circle my answer. And how does that compare to how fast it was going before? Okay. Well, it was going at 8 times 10 to the second. So now it's going at 1.78 times 10 to the third meters per second. So that's more than double the speed. Okay, more than double the velocity, actually, I should say. Okay, because this times 2 would be 16 times 10 to the second. That would be 1.6 times 10 to the third. So we've more than doubled the speed by expelling this much gas. So this is a great example of conservation of momentum in intergalactic space, right? And I was a little tricky about making the fuel so significant that it would make an effect on the change. If the fuel, by the way, was in grams and the rocket was in kilograms, then you're pretty much sure that you wouldn't have to do this. You could assume that the mass of the rocket would be the same before and after, right? But in this case, I deliberately designed it so you could not do that, so that you had to take into account the change in mass. So that makes this one especially tricky, and I can see why people might not have done that. Now, if you didn't do that and you had a 4.2 there, don't you see that that would make a significantly different result? It would have changed the result significantly. Let's see, what percentage would that change it? 4.2 divided by 3.6, that would have been a 17% difference, which is a significant difference in your answer, okay? So anyway, that's the first example. So here is our next example. It's another one of these kind of problems, right? Okay, this time it's a cosmonaut. A cosmonaut at rest fires a thruster pistol that expels 20 grams of hot gas at 2,000 meters per second. The combined mass of the cosmonaut and the pistol is 150 kilograms. How fast and in what direction is the cosmonaut moving after firing the pistol? Okay, so which one of these are we going to have to use again? Which one are we going to have to use? Well, it is about conservation of momentum. It is about all this, but at rest. Okay, that's the important thing. So if we're starting off at rest, that means the initial velocity equals 0. So if that equals 0 and if that equals 0, these sides collapse to 0. let's try to derive the recoil equation from the conservation of momentum equation. Okay, but we've got to change the A's to C's and the B's to D's. So let's just do that first. I'll rewrite this exact equation with MC VCI plus MD and VDI equals MC and VCF plus MD times VDF. Okay, so now the thing about this is that if we put in zero velocity, so if this is 0, okay, and then you're still going to have MC and MD, but they're both going to be multiplied times 0, right? So do you see how, first of all, that this side drops to 0. So 0 times something is 0, and then this is also 0. So then that entire side of the equation is equal to 0. So then what we have to do is we have to try to isolate for one of the variables. So it depends on which one we're solving for. But you can see that in the case of this equation, they solve for VCF. Okay? So why don't we solve for VCF, try to get everything else on the other side. Okay? So if we want to get rid of its neighbors, we have to subtract both sides by this. So what we wind up on this side is negative. If we subtract MD VDF from both sides, we get negative MD VDF. That's where that negative comes from. And that equals still MC VCF, right? And then we have to divide both sides. We have to divide both sides by MC. And if we divide both sides by MC, what we wind up with is negative MD over MC times, I'm writing it a little bit more like this, VDF equals, and then these cancel out, and you are left with VCF. Now, of course, this is backwards, so let me just rewrite the other way around. So VCF equals, and then these are put into parentheses, but notice that we could have put the negative outside the parentheses if we wanted to. It's just by convention that they put it in there. So I'm going to write it slightly differently. I'm going to put the negative sign here, and then in the parentheses, I'm going to put the MD over the MC, and then I'm going to put the VDF. So now, that is the same equation. The only difference is I would like to put the negative on the outside of the parentheses just so it doesn't make it look like there's sort of a negative mass. It just seems weird to me. But this is sort of one of the conventional ways to write it. So notice how this equation comes out of this one. Got it? And once you've got this equation, it's very convenient. But remember, you can only use this if these velocities were 0. Okay, so here we go. So let's use the recoil equation. So what are we going to define? The cosmonaut is going to be C. Oh, that's convenient. So the cosmonaut is C. The hot gas coming out of the pistol is going to be the D. That's the D. Okay? So we're solving for the cosmonaut's final velocity. So that's what we're solving for. We're solving for the VCF. And what we're going to put in are the masses. So I'm going to do it my way in this case. I'm going to put the negative sign here, and then I'm going to put the masses in because it just seems to make more sense to me. Okay. The mass of D, which is the hot gases, goes on top. Well, that's 20 grams. Oh yeah, but 20 grams multiplied by 1 kilogram over 1,000 grams equals, so you divide it by 1,000, and that means really that you move the decimal once, twice, thrice, so there'd be a 0 there, so you would wind up with 0.020 kg. So notice how I did that? And it's a very easy conversion. You just move the decimal over 3 times. And don't forget to write this 0 before the decimal, by the way. So that goes right here. That's the mass of the hot gases. And then the other mass, the mass of the Cosmonaut and the pistol, 150 kilograms, goes on the bottom. And then do we know the velocity? Do we know the velocity of the hot gases? Okay. Yes, we do know that. And that is 2,000 meters per second. That just sounds fast, right? So then if we just multiply these all together, it should come out correctly. Now let's first of all, let's do these first. Now we're dividing a small number by a big number. So this is going to be exceptionally small, this first portion here. So what I'm going to do is I'm going to write VCF, and I'm going to put equals. I don't want to forget about this negative sign, so I'm going to put in that negative sign. It'll still be negative, right? Okay. So 0.020 divided by 150 equals, very small number, 0.000133. So you're saying, Mr. Pemble, why are you keeping all those digits when usually you round way over here? That's because, remember, in scientific notation, if the decimal were there, that would only be to the hundredths place. Oh yeah, what's my unit now? Don't fall for that trick again. Look what happens to the kilograms. There's no unit. Unitless ratio, alert, alert, klaxon. Okay, then we multiply that by 2,000. Well, that's going to blow the number up again, make it bigger again. Okay, so then we take, it's still on my calculator. I didn't round it on my calculator, but it shouldn't make too much difference. Times 2,000 equals, what is that? It equals, not a huge number, but velocity CF of the Cosmonaut equals, it's still negative, and now it is 0.2, I'm going to keep 67. It goes 2666. Okay, so 267. What are my units? This had no unit. This has meters per second. Okay, so that is my answer. Oh wait, scientific notation. Scientific notation. So in scientific notation, we need to move the decimal back that way. So this is an interesting one, because not only is the number actually a negative number, right? But notice what happens. When I move the decimal that way, okay, 2.67, that's why I kept all the way to there, because I knew that would be the hundredths place in scientific notation, times 10 to the, what would it be? What would it be? Is it to the first? To the negative first. Meters per second. Don't forget to write your units. So isn't this funny? This is actually a negative velocity with a negative exponent. This, however, doesn't really make it negative. This just means that the value was less than 1. Notice how this is less than 1. That's what that means. This means that it's really negative. So if we define the notice that we have defined the direction that the gas was going as positive, because this was a positive number. So if you define that as positive, which we didn't even mention that we did that, we didn't even maybe notice that we did that, if that's positive, well then the other direction must be negative. So the Cosmonaut is actually going in a negative direction and not moving too fast. That doesn't seem so fast if it's a number less than 1. And then boom, 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 circle your answer. That would be your answer. Okay, so that's another example of recoil. And now you can see how recoil comes out of the conservation of momentum. It's a specific example when you start at rest. Thank you.